Welcome back to the deep dive, where we take the most complex research, the densest papers, and really try to extract the pure, vital insights.
And today we are wrestling with, I think it's fair to say, the ultimate question in science and philosophy.
Consciousness itself.
It really is. It's the mystery that scientists have tried to solve since the beginning of modern neuroscience. Why does the physical activity of the brain, those measurable voltage traces, those chemical pulses,
Right.
why does that generate subjective lived experience? Why does that particular pattern of neural firing feel like the color blue?
We call that gap the hard problem. And while we've gotten really, really good at finding the neural correlates of consciousness, the where and the when of conscious processing, we still lack that fundamental bridge. We have the objective data, which you can think of as a massive high-dimensional data set of brain activity, let's call that $.
Right, the neural space.
And then we have the subjective report. You telling me, for instance, that red is much closer to orange than it is to green. And that's our phenomenal report, our little map of experience. Let's call that straight.
And the problem is precisely this. We've identified the correlates, but there is what the authors of our source material today call a fundamental metric gap.
A metric gap.
Exactly. How do you actually write a mathematical equation that proves no lard and the 30-teller are structurally identical? How do you prove that the shape of the brain activity is the shape of the feeling?
That is our mission today. We are dissecting the Phenomenal Manifold Hypothesis, or PMH.
As put forth in the, I think, truly revolutionary 2026 paper, The Topological Signature of Consciousness by Eric Race.
And the claim here is that the theory doesn't just look for correlates. It sort of bypasses the need for functional explanations altogether.
It reframes the mind-body relation entirely. It moves it away from this, metaphysical duality and turns it into a testable problem of metric space alignment.
Metric space alignment. So just lining up two different kinds of maps.
That's the core radical idea, that consciousness is a geometric structure.
So instead of asking what causes consciousness, we are asking, is the geometric structure of the brain isometric? Is it mathematically identical to the geometric structure of experience?
We are diving into the geometry of qualia.
Okay, so before we get into the really heavy math, and I know it's coming, we have to appreciate why this reframing is even necessary. Let's expand on that metric gap.
We have to, because if you look at neuroimaging data, fMRI, EEG, you get thousands, millions of measurements per second.
Right. It's this incredibly high-dimensional cloud of data. You get voltage traces, BLD signals. This is the neural space, knowledge.
It's objective, it's observable, and it's messy. It's noisy.
It's incredibly messy. But on the other hand, phenomenal space is derived from psychophysics.
So those are the subjective similarity judgments we were talking about. If I show you two shades of blue and ask, how different are they on a scale of 1 to 10? Your answer, quantified, creates the structure of space.
And that space is fundamentally low-dimensional, and it's relational. It's all about this is closer to that.
And existing theories, for all their power, really struggle to bridge this structure gap.
Let's take integrated information theory, IIT. It gives us a scalar measure, a single number.
It's a number indicating the amount of integrated information present. It's powerful, but it tells you the size of the conscious container, if you will, not its shape.
And what about something like global neuronal workspace theory, GNWT?
GNWT is fantastic for explaining the access mechanism, how information gets broadcast globally to become conscious.
The ignition event.
The ignition, exactly. But both are essential descriptions of necessary conditions, but they stop short of modeling the intrinsic geometry. As Race notes in the paper, they do not explicitly model the intrinsic geometry of phenomenal space.
So they might tell us that we are conscious or how we become conscious of something.
But they don't explain why the experience of hue, of color, should form a closed, continuous loop. A circle, topologically in Esmonasher.
They don't explain why pitch feels linear, or maybe helical, or why pain organizes in this very specific localized geometry.
It's the container size and function versus the actual shape of the contents.
And that is where the PMH comes in.
The PMH directly addresses this structural organization. It posits that the structural relations we perceive in our phenomenal space, in OSS, are structurally isomorphic. They have the same shape as the information theoretic relations in the neural space, knowledge.
Okay, that is a huge claim. To back that up, the paper leans on a pretty deep philosophical anchor, Ontic Structural Realism, or OSR.
It does, and we have to talk about this because it's the move that allows the hard problem to just dissolve.
Okay, for our listeners, that sounds like something pulled straight from a graduate-level physics textbook. Can you break that down for us? What does it mean, and why is it so critical here?
Absolutely. OSR is a philosophy of science that says structure, not substance, is fundamental.
Structure, not stuff.
Exactly. Forget about what the stuff is made of for a second. Quarks, neurons, silicon chips, whatever. OSR claims that the things, the substance, are actually derivative of the relational structures they participate in. The relationships come first.
I'm going to need a strong analogy here. If I look at a complex symphony, the individual notes, the A flat, the C sharp, are the substance. What's the structure?
The structure is the score. It's the relationship between the notes. The rhythm, the harmony, the timing, the counterpoint. A symphony remains the same symphony whether it's played by a massive orchestra,
Right.
synthesized on a computer, or even just hummed softly by one person. The underlying physical medium, the wood, the copper, the silicon, the vocal cords, it all changes.
But the relational structure, the score, is invariant. It's the same piece of music.
Precisely. And OSR says the score, the structure is the reality. The physical instruments are just different manifestations of that same essential structure.
Okay, so now apply that to the mind-body problem. This is the big leap.
If the relational structure of the neural manifold, Mahler's, is mathematically identical, if it is isometric, to the relational structure of the phenomenal manifold, then according to OSR,
Yay.
they are physically identical.
There's no difference.
There is no difference. The brain structure is the experience structure. You don't need a magical leap from one to the other.
Wow. That's a powerful move because it completely bypasses the need for a separate explanation for the feeling.
Yes.
We aren't asking how electricity becomes a feeling anymore. We're asserting that the pattern of electrical relationship is the pattern of phenomenal relationship.
The qualities of experience, the qualia, are therefore defined purely by their geometric location and their relational pattern within the Azia.
So the feeling of red isn't some mystical intrinsic property of red.
No, it is the unique position and distance of that point relative to all other colors, orange, purple, green, within the geometric structure of the color manifold.
If 2 points are close in that space, the experiences feel similar, the geometry is the quality. This just dramatically changes the nature of the inquiry. It moves the hard problem from a question of metaphysics, how does matter feel, to a problem of mathematical proof.
A solvable problem.
A solvable problem. Can we find an isometry between this high-dimensional neural graph and this low-dimensional phenomenal map? It makes it testable.
And that's the whole game.
So the challenge now is, okay, how do you construct these two spaces mathematically so they can actually be compared? Let's start with the neural space, NALR.
Okay, so the neural space, Na-dollar, is the theoretical manifold of all accessible neural states. This space needs an intrinsic measuring stichometric that defines distance within the brain. Rees proposes using the Fisher information metric, or D-dollars.
The Fisher information metric, why that one specifically? I know metric just means a way to measure distance, but why this particular one? What does it capture?
It's really the perfect choice because it's an information theoretic distance. It doesn't measure physical distance, like millimeters in the cortex.
Right, it's not a rule.
It's not a ruler. It measures the distinguishability of probabilistic codes. You have to think of the brain as constantly running billions of tiny statistical comparisons. The Fisher information metric quantifies how easily the system itself can distinguish between two slightly different patterns of neural activity.
So if two neural states are firing in very similar but not identical ways, and the Fisher information metric gives a small number,
it means the brain has a hard time telling those two states apart. They represent very similar information.
Got it. It's the brain's own internal ruler for information fidelity. If the distance is large, the brain easily differentiates the two patterns.
Precisely. This makes the Dullar's measure of the system's intrinsic capacity to represent distinct information. And that's a crucial first step toward defining consciousness.
Okay, so that's one side. On the other side, we have the phenomenal space with its own metric. This is the one derived from our subjective reports, the Weber-Fechner distances perceived dissimilarity.
And the challenge is connecting the two. And this is where the paper introduces its main constructive mechanism, the hybrid phenomenal metric, which they call GRV.
Okay.
This metric is the constructive definition of what phenomenal structure is. The brain structure doesn't just passively become experience. It is actively shaped by the current state of consciousness.
I'm looking at the mathematical formula in the source material. GITI, GRGI plus HI gamma delta, and that looks incredibly intimidating.
It does.
So instead of hitting us with all the math notation, can you break down the two major functional components for us? What are the foundation and what are the modulators?
Great question. The formula looks scary, but the concept is actually pretty manageable. It's saying that the total structure of your experience, GRB, is built from two main parts.
Okay.
The first part, GRBA, is the foundation. That is the raw structural information inherited directly from the neural system. It's that Fisher information metric interest sort of pulled back onto the phenomenal space.
So that's the structural blueprint. It's the raw template from the neural side. The brain's capacity to differentiate information sets the starting point.
Exactly. But, and this is the key, that blueprint is then modulated by the second component, that $I gamma delta term.
Okay.
This is the structural deformation tensor. And it depends on three global invariants. These invariants define the volume, the fidelity, and the coherence of your current conscious state. Think of them as the volume knobs that shape the final manifold of your experience.
Okay, let's dedicate some serious time to these knobs, because this sounds like it explains why our experience shifts so dramatically when we move from, say, deep sleep to focused wakefulness.
It's the entire mechanism. So the first knob is integration, dollar. This ensures topological connectedness.
Connectedness, meaning what?
Meaning that if dollars is high, the experience is unified. I perceive the color, the sound, and the touch of this microphone as a single coherent moment. One thing, if a dollar drops drastically, the phenomenal structure fragments into unrelated bits of information. This is the difference between a unified consciousness and potentially a dissociated or pathologically fractured state.
Okay, that makes sense. What's the second knob?
The second is coherence, gamma, which the paper identifies with the Kuramoto order parameter.
Which is a measure of synchronization across the system. I know that one from physics.
Yes. Gamma is the binding constant. It measures the degree of phase synchronization in the neural oscillations. A high gamma means the manifold is structurally coherent. The parts all relate to each other correctly.
Give me an analogy.
Imagine you're trying to assemble a complex 3D model from laser-cut pieces of wood. High gamma means all the pieces snap together perfectly, the angles are right, and you get a unified object.
Unified qualia.
Exactly. Now, if gamma goes to 0, the metric structure degenerates. The pieces don't fit. The experience loses its integrity and coherence, potentially leading to something like visual fragmentation or temporal confusion.
And the final knob is differentiation, which is linked to the entropy of the neural repertoire.
This is what gives the manifold its volume.
Volume, so lividness, richness.
This is perhaps the most intuitive one. High delta means the system can access a vast and complex array of possible neural states. It has high entropy. This corresponds to wakefulness, focus, and vividness.
Okay.
When deltas is high, the phenomenal manifold expands, allowing for long geodesic distances between points. You can clearly, vividly distinguish red from crimson from scarlet.
But if deltas is low,
the manifold is squashed. It contracts, reducing the capacity for differentiation.
So the PMH allows us to model the fading of consciousness not as some binary on-off switch, but as a dynamic geometric process. It's a collapse of the manifold.
Precisely. Let's take the paper's example of the geometry of color. Color space is a complex 3D shape, but hue itself is a loop in $20. Race uses the model where the radius, the dollars of that color manifold, is proportional to the log of differentiation. Delta is proportional to log plus delta points.
Okay, let me walk through the consequence of that. If I'm getting drowsy, or maybe under mild sedation, my differentiation, my delta, drops significantly.
And as delta drops, that radius trawler collapses towards 0. The manifold literally contracts toward its central axis.
So the topological feature, the loop, the fact that hue eventually wraps around on itself, that might still exist conceptually.
The topology might persist for a while.
But the metric volume vanishes. The size of the loop shrinks to nothing.
And experientially, what does that feel like? The vivid colors fade toward the center of the color space, which is grayscale.
The ability to distinguish red from pink just vanishes because even though they're technically different points on the structure, the geodesic distance between them, the measure of difference, becomes negligible.
It's a literal shrinking of your capacity for subjective experience. The distinction becomes too small to measure phenomenally. Total color blindness, achromatopsia, would be the extreme endpoint of this collapse, defined purely by structural geometry.
This reframing is incredible because it gives us a precise, measurable geometric definition for states like drowsiness or even pathological states like seizure activity.
Right. In a seizure, you might have high coherence, massive global synchronization.
But if the diversity of states, the differentiation collapses to near zero, the result is still a collapsed non-phenomenal state.
The volume necessary for experience vanishes. The geometry requires a balance. You need high dollars for connectedness, high gammas for coherence, and high delta for volume, all to get rich, unified, wakeful consciousness. Any collapse in one of these parameters means the phenomenal manifold structurally fails.
Okay, so we have meticulously built both sides of the bridge. We have the high-dimensional noisy neural space, defined by the Fisher information metric, and we have the low-dimensional phenomenal space, defined by that hybrid metric sphericide.
Right.
But here is the massive practical hurdle. They are measured in completely different systems, different units, different coordinates.
It's the map problem again. We have a neural map drawn on some high-dimensional surface, defined by voltage and information flow. We have a phenomenal map, drawn by subjective reports, defined by perceived similarity.
You can't just overlay them and look for overlap. It would be meaningless.
It would be nonsense. We need a tool that ignores the coordinate system entirely, a tool that only compares the intrinsic relationships within each map.
Enter Gromov-Wasserstein.
Enter Gromov-Wasserstein, or GW, Optimal Transport Distance. This is the mathematical key that unlocks the entire PMH. GW is a measure of structural similarity between two metric spaces. It is, and this is a bit of a mind bender, a distance metric for measuring distances between distances.
Okay, walk us through the analogy again, but let's make it really concrete.
Imagine you have two atlases. Atlas A is a highly detailed 3D topographical map of a mountain range. Distances are in miles. Atlas B is a flat, simple tourist sketch showing hiking times between huts. Distances are in hours.
Completely incompatible. The units are different, miles versus hours. The projections are different, 3D topography versus a 2D sketch. The scale is all different.
Exactly. If you try to compare the X and Y coordinates of a city in Atlas A with the X and Y coordinates of the same city in Atlas B, you will get complete garbage.
Right.
But GW doesn't care about coordinates. It asks a different question. It asks, if city A is twice as far from city B as city C is from city D in Atlas A, is that proportional relationship preserved in Atlas B?
It's comparing the internal relationships, the ratios of distances.
It's finding the cheapest way, the optimal transport, to morph the distance matrix of Atlas A onto the distance matrix of Atlas B, minimizing the distortion required to align their internal relational structures.
So in the context of consciousness, we are comparing how distinguishable two neural states are, $80, with how different two experiences are perceived to be.
And the math, formalized in what the paper calls Proposition 3.1, is the entire claim of the PMH. If the Gromov-Wasserstein distance between 9 and Alice Tabors is approximately 0,
GW1 approximate.
the two spaces are declared isometric. They are structurally identical.
The hard problem is mathematically dissolved.
That's the claim.
This sounds almost too elegant. If they are structurally identical, we have found the bridge. But the real power comes from what the process of finding this minimal distance yields, right? It's not just a number.
That's where we move beyond mere correlation and find the geometric neural correlate of consciousness, the NCC.
Okay.
When GW finds the optimal alignment, it doesn't just give you a cost. It generates an optimal transport plan, which they call gamma. This plan is the functional map.
The transport plan, gamma, is the key. It tells you exactly which specific high-dimensional neural states in $none must be grouped and mapped to which low-dimensional points in phylae to achieve that minimum distortion.
Yes. The support of gamma identifies the NCC. It doesn't just say, oh, the NCC is somewhere in this brain region.
Oh.
It says the NCC is precisely this set of 50 neurons firing with this specific relational pattern, because that pattern, when measured intrinsically, perfectly matches the structural relations of the experience itself. It moves the NCC from a statistical observation to a geometric identity.
So we've gone from asking, are these two things correlated, to asserting, this neural activity is this feeling, and here is the mathematical proof of their shared geometry.
It's the most rigorous test of structural identity that has been proposed yet.
Okay, but now we have to address the natural skepticism that arises when you're dealing with such sophisticated mathematics. I'm talking about the manifold illusion critique.
And you should. It's a crucial point.
Right, because this is where I, as the skeptic, step in. If I take enough random high-dimensional data and I apply powerful dimensionality reduction tools, things like UMA or isomap, I can almost always find beautiful, clean shapes. I can find loops, clusters, curves.
You can find structure in noise.
You can find structure in noise. So how does race prove that the structure found through this GW alignment is a genuine intrinsic feature of the physics and not just a statistical artifact of the algorithm that's designed to look for patterns?
This is the essential check, and it's handled by bringing in an entirely independent set of mathematical tools, topological data analysis, or TDA.
TDA.
And specifically, a technique called persistent homology. TDA is great because it ignores metric distance entirely. It only looks for stable, robust structural features. It looks for the holes in the data.
Okay, explain persistent homology using an analogy that will stick with our listeners.
Think of a piece of Swiss cheese, riddled with holes. Persistent homology is like gradually thickening the connections between all the points of dipping the cheese in wax layer by layer.
Okay.
At first, all you see are individual points. Those are the beta-dollar components.
Yeah.
As you thicken the connections, you start to see the tunnels and the loops. Those are the beta-letter features.
So the hole in a donut would be a beta-letter feature?
Exactly. And if a feature or tunnel persists across many scales of wax thickness, you know it's a fundamental intrinsic hole in the cheese. If it only appears fleetingly for one thin layer and then disappears, it's just statistical noise.
So persistence is the key. And the Betty numbers, Betties, they just count these features. Beta dollars is the number of connected pieces. Beta doll is the number of loops or tunnels. And beta 2 would be the number of internal voids or cavities, like the hollow center of a sphere.
Correct. And a genuine phenomenal manifold must exhibit stable features. This leads to what the paper calls criterion 3.1 for topological authenticity.
And that criterion says you have to compare the topological features of the real structured data against phase-shuffled surrogates.
Yes. You take your neural data, you scramble the firing times, but keep the overall firing rates the same. This destroys the relational structure, but preserves the raw statistics.
It's the control group.
It's the perfect control. The structured manifold must generate what's called a persistence landscape, a quantitative measure of how deep and stable those loops are that is significantly greater than the landscape of the scrambled control data. If the structure is real, its topological signature must stand out massively from the noise floor.
So this sets up a brilliant dual validation. You use GW to prove the metric alignment is good.
And you use TDA to prove the structure you're aligning to is not just an illusion.
And this dual pipeline was put to the test using the proof of concept in the paper, the coloring experiment.
This is where it gets really concrete.
Let's detail this, because this is where the theory shifts from, deep philosophy to actual empirical science.
So the target, the ground truth phenomenal manifold, was kept simple. A unit circle, 7 on 1, that represents the continuous loop of hue perception.
Right. Red flows into orange, into yellow, and eventually violet flows back into red. It's a circle.
And the goal was to prove that the neural data, null-IR, could be reliably mapped to this loop.
And the neural model, null-IR, was deliberately made difficult. It was noisy.
Extremely noisy.
Yeah.
It simulated 50 neurons with Gaussian tuning curves, which is standard, but then it was corrupted by high Poisson noise.
Yeah.
They essentially buried the signal in static.
So they weren't making it easy on themselves.
Not at all. They then compared this noisy, structured neural model against two things: the clean 7-1 target and a control model made of rate-matched shuffled spike trains.
The scrambled data, which has the same noise and activity levels but lacks that coherent circular relational structure.
Exactly. So if the PMH works, the GW alignment cost between the noisy but structured $9 and the clean tights should be near zero.
While the cost between the scrambled control and peaky should be much, much higher.
And the results were definitive. First, the TDA successfully recovered the expected circular topology for the structured data. The bet of a 1 count was 1.00. The loop persisted, even with all that noise.
Okay, so the shape was real. What about the Gromov-Wasserstein cost, the measure of distortion?
The structured neural model showed a normalized GW cost of 0.042 PM.0051.
That's a tiny number.
It's incredibly low. It confirms near isometry. To put that back into our map analogy, the distortion required to morph the neural map into the phenomenal map was tiny, like comparing two photos of the same room taken from slightly different angles.
Okay, now compare that to the shuffled control, the noise that maintained the raw statistics but lacked the underlying structure.
The control model yielded a cost of 0.35 cent PM.
Whoa.
It's a massive, highly significant statistical difference with a p-value less than a 0.001. The distortion required to force the shuffled noise into the shape of the color ring was nearly 10 times greater.
That is the smoking gun.
That's it.
It proves that the GW-TDA pipeline is specifically sensitive to genuine intrinsic phenomenal geometry. It rejects the manifold illusion by demonstrating that the algorithm finds the structure embedded in the neural firing, not just patterns in random noise.
The circular geometry of hue, which you experience every day, is demonstrably present in the relational firing of those 50 simulated neurons. This moves the PMH out of the realm of speculation and into verifiable computation.
We can now, in principle, look at a piece of neural data and mathematically determine the shape of the experience it generates.
That's the promise.
Okay, so having seen the structural proof of concept, let's situate the PMH within the broader field. How does this structural geometric approach relate to the leading theories like IIT and GNWT? Is it a competitor? A collaborator?
That's a crucial question. And I think it's important to see it as being focused on a different aspect of the problem. It's focused on the qualitative geometric nature of consciousness, whereas its predecessors focus more on quantity or mechanism.
Okay, let's start with IIT. We know it provides the scalar measure phi, so is PMH a replacement, or does it work with it?
I think they are potentially complementary. IIT tells you how much integrated information there is, the size of the box. PMH tells you the shape of the information inside that box.
Oh, okay.
So a system could have a very high blocks, confirming the presence of a lot of integrated information. But if that system's phenomenal manifold is just a flat plane with no persistent holes or complex curvature, we know what that consciousness must feel like.
It would be simple, undifferentiated, maybe boring.
Exactly. So PMH provides the qualia map, while IIT provides the prerequisite quantity of integration necessary for that map to even exist. Qualia is necessary for the manifold, but the geometry defined by GAP is what gives the manifold its specific phenomenal characteristics, the what it's like.
Okay, and compared to GNWT, which focuses on access and global broadcast.
GNWT is concerned with the function of information. How does it get broadcast to a global workspace to be used by other processes? PMH describes the intrinsic structure of the content that is being broadcast.
So before information can be broadcast globally, it needs to be organized into a stable, coherent, phenomenal manifold.
Exactly. The PMH explains the internal geometric architecture of the contents of the workspace. Without that geometric structure, there's nothing meaningful to broadcast in the first place.
This geometric focus is what makes the PMH highly falsifiable. It generates these very concrete geometric predictions that are distinct from those made by scalar or functional theories. Let's look at the predictions detailed in Table 2 of the paper.
These predictions are the real litmus test for the PMH. If these geometric transformations don't happen in the corresponding states, the theory is wrong. Simple as that.
Okay, prediction 1. Anesthesia and loss of consciousness. PMH predicts a topological phase transition. That sounds dramatic.
It is a dramatic claim. It says that losing consciousness is not just a gradual slowing of neural activity, but an abrupt critical phase change.
Like water freezing into ice.
Precisely. Specifically, the loss of consciousness should correlate precisely with the abrupt collapse of homological cycles. The Betty numbers, $, should abruptly dissolve to zero.
So when a patient goes under anesthesia, we shouldn't just see a slowing of their EEG rhythms. We should see the mathematical structure of the color ring, the pitch helix, and all other qualia structures literally dissolve back into disconnected components or points.
The manifold becomes contractible. It loses all its interesting complexity. That is the test. If loss of consciousness occurs while the Betador loops and beta-2 cavities remain stable, the PMH fails. It requires a direct mathematical link between the structure vanishing and the experience vanishing.
An incredibly precise, time-locked prediction. Okay, prediction 2 is the cross-modal geometric isometry. This aims at a potential unification of sensory experiences.
Right. We've discussed that color hue is a loop, and that says $1. Auditory pitch is often perceived as helical loop that also moves linearly, like a spiral staircase.
They share a structural element, the loop.
And the PMH predicts that if you measure the phenomenal manifolds of these two disparate sensory experiences, they should exhibit near zero GW alignment. So GW should be approximately 0 in the relevant higher-order association cortices.
Meaning the structure of the neural manifold supporting pitch perception should be nearly isometric to the structure of the neural manifold supporting hue perception.
Yes. It's a geometric testable mechanism for what could underlie synesthesia-like phenomena. The structure of one sense is mathematically identical to the structure of another.
And prediction 3, which is maybe the most exciting one for its philosophical implications, the geometric interpretation of the psychedelic state.
The PMH predicts two things here. First, a massive manifold expansion. The differentiation invariant, delta, should spike, which increases the volume form and the curvature of the manifold.
Which aligns perfectly with subjective reports of heightened vividness, complexity, the ability to distinguish far more states than normal.
The system has a geometrically larger space to operate in.
But the truly profound prediction is the creation of novel topological wholes, Betech-Nallers.
This is the wild one. If the geometry expands and warps sufficiently, the system could cross a threshold where it creates new loops or new cavities that simply did not exist in the baseline state.
And this would provide a geometric mechanism for novel or dissociative experiences, qualia, that the system was previously structurally incapable of generating.
Exactly. So when someone reports experiencing entirely new colors or sensations that defy description, a sensation that can't be placed on their normal phenomenal map, the PMH suggests those experiences correspond to geometrically new features.
A new beta-1 loop, a new beta-2 cavity. The system has literally changed its geometry to allow for a new form of reality.
It explains the novelty of those experiences not as random firing, but as a predictable structural reorganization of the phenomenal manifold itself. The experience is structurally new because its underlying mathematical architecture is new.
Okay, before we wrap up, we have to address the limitations. No theory is perfect, especially one this ambitious.
And the author is very transparent about three major challenges. First, computational complexity.
Right.
The Gromov-Wasserstein computation is notoriously difficult. It's NP-hard for large data sets. Scaling this proof of concept from 50 neurons to the human brain with billions of states. That requires serious algorithmic breakthroughs and major computational resources.
Second, the current formalism is static. It treats conscious states as individual snapshots in time.
And consciousness is dynamic. It flows. To accurately capture that temporal flow, the geometric framework would need to be extended into time-dependent geometry, maybe involving something like Lorentzian manifolds, where time itself is integrated into the metric structure.
That's cutting-edge mathematical physics, far beyond the current scope.
Far beyond. And finally, the construction of the phenomenal space, BASI itself, it still relies on subjective reports, behavioral input,
which are inherently noisy, potentially unreliable, and may not fully reflect the true intrinsic phenomenal structure.
It's the perennial constraint of consciousness research. You always come back to the report. However, by providing a robust mathematical framework that makes verifiable geometric predictions, the PMH gives us a highly rigorous way to refine that behavioral data and test its structural fidelity.
It provides the unifying language we needed to bridge information theory, neuroscience, and subjective experience.
I think so.
So we began this deep dive with the hard problem, this massive gap between matter and feeling. The Phenomenal Manifold Hypothesis closes that gap not with a philosophical guess, but with a mathematical proof. It shifts the question from why does stuff feel like anything to a concrete geometric challenge. Can we prove the shape of the brain is exactly the shape of the feeling?
And the tools Gromov-Wasserstein alignment and persistent homology provide the affirmative answer and the rigorous verification needed to avoid illusion.
Consciousness, in this view, is not a mystical force. It is the intrinsic topological signature of a highly integrated information system.
The hard problem is successfully reformulated as a tractable problem of structural alignment.
This focus on geometric structure moves us past just measuring how much complexity is present to actually creating a map of the experience itself. It gives us the framework to study what the subjective world looks like mathematically.
And this leads us to the final provocative thought this framework raises for you, our listener, to explore. We demonstrated that the color ring model successfully recovered a persistent one-dimensional loop, a beta-1 or for hue. But what would it signify, scientifically and philosophically, if empirical neuroimaging were to discover a persistent stable two-dimensional cavity, a Betty number beta-2 1-1-1 in the human phenomenal manifold?
A stable void. That would mean there is an intrinsic topological hole in the structure of reality as we perceive it, a geometric feature we can't currently map to any known sensation.
Exactly. What new, unimaginable subjective reality, what totally alien form of qualia would that persistent geometric cavity correspond to?
That is the next great uncharted territory this topological framework challenges us to explore.